Since the beginning of humankind, people have wanted to know about our place in the universe.
Where we came from, what is our history? How did the universe around us evolve?
The amount of data we have, the amount of knowledge that we've been able to accumulate just very recently is really astounding.
Thanks to this satellite, the Wilkinson Microwave Anisotropy Probe, or WMAP.
It maps the microwave radiation across the whole sky.
The cosmic microwave background radiation is light left over from the Big Bang that gave birth to the universe.
Coming from when the universe was 380,000 years old.
Within this microwave radiation lies the very DNA of the universe, the key to unlocking its mysteries.
And it's like a fingerprint to us.
We can use these observations to learn a lot about the basic properties of the universe. What's the geometry of the universe? How old is the universe? What's the universe made of?
Questions no one has ever come close to answering with pinpoint precision until a team of American scientists banded together in the 1990s, headed by this man. Dr. Charles Bennett, astrophysicist, Johns Hopkins University, Baltimore.
I first encountered this equation in freshman physics.
Bennett teaches astronomy and physics. Before taking this job in 2005, he worked for the National Aeronautics and Space Administration, or NASA, for 20 years. In 1989, he was deputy chief of one of the 3 experiments of a satellite mission to study cosmic microwave background radiation. Later, to study the CMB in finer detail, NASA teamed up with Princeton University scientists to design and build the WMAP satellite.
I was in charge of the entire project. Every day, I pretty much would get a phone call that usually started with the words, "Chuck, we have a problem." And it could be anything. It could something that stopped working. It felt like the old story of pushing a boulder up a hill.
But his biggest worry was sending the satellite to its destination. The second Lagrangian point, or L2, 1.5 million kilometers from Earth.
The satellite has tiny little rockets built on it, and there's a fuel tank in the middle of the satellite, and computer figures out how much of each of these rockets needs to fire for how long to get us there. So we had the satellite go in 3 loops around the Earth as we carefully adjusted and burned our little rockets to get the timing just right. So the satellite would just swing by the moon and then pick up some energy from the moon's gravity, basically.
And propel the satellite to L2, where it would observe cosmic microwave background radiation. June 30th, 2001, the day of reckoning.
Ready. SSP. Ready. ACC. Ready.
And I was in that control room at the Kennedy Space Center during launch.
10, 9, 8, 7.
And so I'm just sitting there, nervous.
3, 2, 1. Main engine start. And liftoff of the Delta II rocket with the MAP spacecraft. Exploring.
Well, if we didn't get to where we were going, it would have been the end of the mission.
Guidance system has started.
WMAP reached its destination without a hitch 100 days later, but Bennett paid a high price for such a feat. Four days after the launch, Bennett felt intense pain in his back.
I decided maybe I could loosen it up if I exercised. Nothing was making it feel better. So I finally woke my wife up.
So I called the doctor, and the doctor said he could be having a heart attack, get him to the hospital as quickly as possible.
This is approaching 3 in the morning. She got in the car and she drove me to the hospital. And my wife, bless her heart, is a rule follower.
I obey the stop signs. Near the hospital, even though it was 3 in the morning, there was a red light. I stopped. Chuck yelled at me not to stop for the red light. There's nobody anywhere. You just have to run the red lights. Yeah. No.
Bennett underwent surgery the same night.
My gallbladder was apparently 10 times the normal size, and gangrene had set in.
Hello.
Where are we going?
Silk Road.
Silk Road.
You had your good workout this morning at the
I
gym?
had my good workout at the gym. Not as good as I would have liked, but it was at least a workout.
Bennett's wife, Renee, is a political science professor, also at Johns Hopkins University. They both studied at the Massachusetts Institute of Technology in Boston and met at a Jewish religious service.
I am pretty observant with Judaism. At MIT, and a friend of mine said, why don't you come to the Conservative Reform Service? And I said, Jeannie, there are no socially acceptable male graduate students at MIT. She got me to come. And I looked around, and every male looked completely scruffy. Beard unshaven, hair a mess, shirt tails out. There was one guy whose beard was neatly trimmed and his shirt tails were tucked in. And I turned to my young friend and I said, I'll take him. And that was Chuck. And he
I don't know what happened.
He never knew what hit him.
The couple have 2 sons.
This one's the spicy one, right?
Yeah, I needed chilies and I didn't have any fresh, so you can see the spicy tomato.
You know, I was raised in a culture of science. My father was a physicist, and my 2 hobbies were astronomy and ham radio. I've been interested in the cosmic background radiation since my early years in high school. So 35 plus years I've been interested.
It's complete obsession.
Yeah,
It turns out his calibration's what matters.
Davis Spergel, chair, Princeton's astronomy department and WMAPS theorist. His job was to interpret the data.
What we're measuring is its intensity. Is it brighter in one part of the sky or dimmer?
The CMB's intensity is one indication that region in the sky is dense with matter, the seeds from the birth of the universe that later evolved into stars and galaxies.
Space itself being a pond. The early universe is very much like that calm wake. These hot and cold spots are ripples in the sky. So if you imagine dropping rocks into water and to oil, the pattern of ripples are different in water than in oil. So by looking at the pattern we see on the sky, we can figure out what's the universe made of, in a sense, water or oil. Not only that, we can see whether we were throwing in pebbles or rocks or boulders. We can use these observations of the small temperature and density variations to learn a lot about the basic properties of the universe.
The WMAP data fit what is now known as the standard cosmological model of the universe. Age, 13.7 billion years. Geometry, flat. Composition, 4% atoms, 23% cold dark matter, and 73% dark energy. What stunned physicists is the WMAP's precision.
that it has precisely measured the composition of the universe, and it's redirected a lot of the work in particle physics towards finding out the properties of this dark matter and dark energy.
Scientists are now scrambling to figure out what cold dark matter and dark energy are.
Dark matter surrounds us at this very moment. It's passing through you, passing through me. It just doesn't interact very strongly with us. So dark matter is matter like ordinary matter in that it gravitates, but it's dark. It doesn't emit light. Before WMAP, we knew that there was dark matter. We had some indications of dark energy, but the precision and the beauty of the WMAP results swept away all the doubts in the minds of many physicists, me included.
The WMAP has also reinforced the inflation theory that the universe underwent an incredible period of rapid expansion from submicroscopic to astronomical size.
We were able to see the patterns of temperature fluctuations and polarization fluctuations that were predicted. And to see that confirmed was very exciting.
Spergo has worked in Princeton for 22 years.
I first came here when I was 17 as an undergraduate, and then went off to Harvard to get my PhD. Spent a year at Oxford, and then came back here.
Spergo learned he won this year's Shaw Prize for Astronomy, along with Bennett and Page, just days before his surgery for thyroid cancer in July.
I was actually up in the middle of the night worrying a bit right before my surgery when I got the email about the Shaw Prize.
He's now undergoing radiation treatment to remove the cancerous cells in his throat.
So this is a radiation detector. So you can see that's the level in background. And because of the cancer, I'm getting, I swallowed some radioactive iodine. It's now sitting in my thyroid area. You can hear there's a lot.
On this day, Spergo is going to get a scan of his throat.
Oh, well, I've been here for 2 surgeries, one in early June, one in early July, and then radiation treatment here last week. The cancer's reminded me of is how little time we all have. How was your day? Time with one's family. Bless her at thou, Lord God.
David and his wife Laura, who's a physician, are both Jewish. They have 3 children.
What was your reaction when David was diagnosed with thyroid cancer?
Disbelief. So I was actually at Newark Airport, fly to a meeting in Atlanta, because all I wanted to do was just fly back home and help him deal with it. He was amazing. I mean, you know, he had the 3 kids and was seeing the patient, you know, seeing the doctors and arranging his surgery and doing all of that, and I wasn't even there to help him for that week.
We had I had very good news this afternoon. As you know, I went for a scan yesterday. So I got the results back on the scan, and I'm all clear. After I got my diagnosis, that I wanted to lose some weight and get in shape. I've been in Princeton for a long time. Intellectually, it's a wonderful place.
A place scientists can lose themselves in their quest to unravel the ultimate mystery, the holy grail of cosmology.
What was there before the Big Bang?
Dr. Lyman Page, physics professor, Princeton University. Page is one of WMAP's main designers. His mentor at Princeton, physics professor Dave Wilkinson, tapped him to help build the satellite. MAP, Microwave Anisotropy Probe, renamed WMAP in honor of Wilkinson after he passed away in 2002.
I was actually walking by the door to this office. This was Dave Wilkinson's office. Dory said, "Hey, you want to work on a satellite?" So I think that was in early '91. I said, "Sure." This is the first version we built. It measures microwave radiation.
Every time we switch channels on a television that uses an antenna, we get what is called TV snow. 1% of that comes from cosmic microwave radiation.
That's why it has this sort of whitish.
Page designed WMAP's optics to capture the signal.
So what happens here is if the radiation, imagine, comes from the sky, comes in, bounces off this, which is the primary reflector, comes up here, then bounces off this element, which is the secondary reflector, and then bounces down into this region where all the instrumentation is.
Page used carbon fibers to make the optics and coated them with aluminum.
And we roughened it so that for that brief instant when we knew that the sun would shine on it, so it diffuses the sun rays, not completely, but enough so we didn't fry the instrument.
To test if the optics could measure radiation accurately, Page bombarded them with microwaves from the math tower over there.
That took us over a year to get right.
WMAP uses 5 frequencies to scan the sky and isolate CMB signal from other sources of radiation.
And what you want to do is turn it into an electronic signal.
This is the universe bathed in cosmic microwaves 380,000 years after its birth, a goldmine of data that would change cosmological concepts forever.
The difference between believing something is true and knowing that it's true.
Coming up, the dawning of a new era.
In the golden age of cosmology.
Princeton University, New Jersey. After 21 years here, Lyman Page has settled down to a routine.
Often after work, just to get some exercise and shed any stress, I just jog from the physics department down by the lake and then back up to home, at least 3 times a week.
He lives near Princeton.
So Kagan was confirmed.
4 of those Supreme Court justices are now from New York.
Overrepresented, right?
Bronx, Manhattan, Brooklyn, and I think Queens.
Lyman and his wife Lisa, also a physicist, have 3 sons.
Is it hard to be in a household of boys? And
Boys they're easy, pretty easy.
Lyman and Lisa studied physics at the Massachusetts Institute of Technology, where they met.
I had a friend in his lab, and so I was going to meet her. He was standing over a dewar of liquid nitrogen, and it was like coming out, and I didn't have any experience with this, so I just asked him if it was dangerous. So that's when I learned that the atmosphere is mostly nitrogen, and it isn't dangerous. So, but anyway, so this was our introduction.
So we're slowly, redoing the house. Every weekend day, I do something on the house just to relax and make things look a little nicer. Growing up, I didn't know what it was about. I mean, I always liked math. I did well in math. And then I think when I learned about physics, I just took a physics course in college. and it was just fantastic. I said, wow, this really makes sense. And I said, this is what I want to do.
Page started researching cosmic microwave background radiation in the 1980s. He's still at it.
This is a list that my graduate students made me for my birthday.
5 years ago.
Buy red Ferrari convertible. So it's published 1 year WMAP data, done.
This is a map of the varying intensities of the universe's cosmic microwave, shown by color-coded spots.
You see there's a dark blue here and a red here. You can see that there's some size associated with these. We measure them all and take the average size. Here's the neat thing. We can compute from first principles how big on average this is. So just using physics. And we can compute it in meters. If we could determine this size here, right? We just divide by roughly twice the speed of light. Since we know the speed of light, we can get the time that light's been traveling to us, which gives us the age of the universe.
13.7 billion years old.
And we know it to fractions of a percent.
When you saw the data the first time, were you stunned?
I don't think I was stunned. I think because we had good expectation. Just in terms of the raw measurement, it's hard to describe how much further ahead it was of anything else that came before it, and how accurate the actual measurement was, and then precision, how much smaller the error bars are. Hey, Jim.
Hi, Lyman.
Good to see you. Welcome back.
Pleasure. Thank you. I call myself a theorist because I analyze the results of measurements. I compute. Lyman I call an experimentalist because he builds the apparatus to make measurements, and then he makes the measurements. Both sides are needed, and very few can work effectively in both sides.
You know, when you're in pain, as we all know, you don't really think about much else. It limits what you can do in terms of using your hand if you have arthritis.
80% of us will experience chronic pain at some point in our lives. Painkillers have become a multi-billion-dollar industry. Some cause side effects, especially if they contain morphine.
There are also problems with addiction.
Now, drug companies are hoping to develop a better way to treat pain, thanks to an American scientist whose research has opened the door for the next generation of painkillers. Dr. David Julius, Chair, Biology Department, University of California, San Francisco. Julius works in this lab.
When we're done with this, probably next week, we should go and see Matt.
His field of research is the sense of touch.
Our ability to detect pressure or light brush, our ability to detect temperature over a wide range from hot to cold.
And our ability to feel pain, the focus of a groundbreaking study Julius began in 1994. What triggers pain and where does it start and end?
If we understand how that works, we can eventually prevent it or suppress it.
Pain warns us of threats to our well-being. But when pain becomes chronic,
rather than being helpful as a warning system, it becomes debilitating.
One of the most commonly used painkillers contain morphine derived from opium poppy. But the drug works on the brain stem that also controls our breathing as well as affects our intestinal muscles.
One of the side effects is respiratory depression. Constipation's another problem.
Is there a way to stop pain with drugs that won't affect other organs of our body? Drugs that would target only the part responsible for detecting pain? Our nerve cells that activate our sense of touch.
So that if you were to develop a drug that affected that site, you wouldn't have to worry that it would be affecting the function of other cells in the nervous system or in the body.
To study how pain works, Julius used the fruit spicy food lovers can't do without, chili pepper.
If you eat a hot pepper, you're in pain. Or if you chop hot peppers and then stick your finger in your eye, this is excruciatingly painful.
Chili pepper contains an active molecule, capsaicin, that causes a burning sensation.
This molecule has a very specific and amazing effect on nerve fibers that are involved in pain sensation.
Nerve fibers are found in many areas of our body, including our eyes, lips, skin, and internal organs. They detect pain, including pressure, heat and cold, or chemical irritants. When the fibers are activated, they send an electric signal up the spinal cord to the brain, which interprets it as a pain sensation.
Is there a specific protein that sits on the nerve fiber and is activated by capsaicin and then initiates this electrical signal so that you can sense this as pain? So we've used the chili pepper extract and capsaicin as the tag to find this protein on the nerve fiber.
For 3 years, Julius tried but failed to make any headway. At one point, he told his wife, Holly, he was giving up.
I looked at her and said, maybe it wasn't, maybe I should just give up. And she looked at me and said, this is going to be really important, so stop messing around and get it done. And I said, yeah, you're right, we should get it done. It was do or die. We were going to hit this problem with whatever approaches we knew we could take.
6 months later, in 1997, he cloned the specific protein that interacts with chili and fires the pain signal to the brain, the capsaicin receptor.
It was one of the first discoveries in the beginning of the use of molecular biology and genetics to really look at pain signaling mechanisms.
It turns out the capsaicin receptor is the same one that detects heat once the temperature goes up to 43 degrees centigrade.
This becomes pain-producing because it's telling you that this could be injurious to your body, to your skin, and you shouldn't be in temperature that hot.
Right after discovering the receptor, Julius phoned his wife.
Holly, how's it going? This is Dave calling.
And he called and he said, I think we have it. I think we got it.
He said, I think we know that.
And I was so excited. And then he said, but don't tell anybody. And I was with my mother. And he said, don't tell your mother.
As a scientist, sometimes you get really excited, but you don't want to tell anybody yet because you could be wrong. And you really want to wait till you're sure. So, Philip, you getting ready for your swim meet on Saturday?
Yeah.
David and Holly have one son.
Did you work on your dive? Because you sort of look like a flying squirrel. Say what?
Holly Ingram is also a biologist at UC San Francisco.
We were at a conference.
At a meeting together, we went to this. There was a very small meeting in Copenhagen, and they sat everyone alphabetically, according to their last name. So Julius and Ingram. So we were sitting next to one another, and that's how we first met. And then after a few minutes, I realized, hey, she's a beautiful woman too, aside from being a good scientist.
David has settled down with Holly in San Francisco, where his wife's family lives.
You're originally from Brooklyn, and what do you like about San Francisco?
San Francisco is a beautiful city, especially on a day like today when it's sunny. It's geographically, it's beautiful. There's lots of rolling hills and vistas. I like being on the water. Even when I lived in New York City, you can go out and do all kinds of things. The other thing I like about San Francisco is that there are some really great academic institutions. UC San Francisco is one of the best biomedical research institutes in the world. For an academic scientist, it's a playground.
The same playground where years later he employed the same technique he used to find capsaicin to identify the protein that detects cold. He used mint leaves.
What makes mint leaves generate a cold sensation is one chemical in them called menthol.
This experiment confirms his finding. This mouse stays only on the right corner, where the temperature is a comfortable 30 degrees centigrade. It avoids the other side, where it's colder at 20 degrees. But this mutant mouse moves between the two sides. A protein in its genes that detects cold was genetically removed.
If this mouse cannot make the protein that senses menthol or senses cold, that this animal behaviorally would not be able to discriminate between a surface that's warm and a surface that's cold.
The experiment has huge implications for treating pain. If a protein that detects stimuli like cold, heat, or pain can be deactivated from firing signals to the brain, pain can be stopped at its source by drugs that won't affect other parts of our body. Drug companies are now doing clinical animal and human trials to develop new drugs based on Julius's research.
So the challenges are to find drugs that modulate the activity of these receptors and quiet the nerve fibers down. But to allow it, we need it to tell us about acutely dangerous situations like sticking our hand in a pot of hot water or hitting ourselves with a hammer. We want to maintain that kind of pain signal. That's a good pain signal. We want to get rid of the pain signal that's inappropriately generated and drives chronic pain syndromes. I would say, without being held to this, that I think the next decade will tell us whether these targets are really good targets for new pain drugs.
With the recent information we have, I think it would be very appropriate.
Roger Nichol, pharmacology professor, UC San Francisco.
What really led to his blossoming as a true scientist was his cloning of this capsaicin receptor. And he has transformed that field from a very descriptive type of science into given it a molecular basis. And the papers that he publishes are noted for their just extraordinary clarity and simply gems.
Should I open it?
Yeah.
Julius has continued to clone more protein receptors, including the one for wasabi, or Japanese horseradish, backed by a staff of 8 researchers.
He's a scientist of great stature, yet he's very personable, and he's actually here in his office with the door always open for us.
Because I guess maybe also ask Clement, the other Clement.
Whenever you have any questions or you have any new ideas, he's more than welcome to discuss it with you. We have like a coffee time at 3. Talk about life, we talk about science.
This is what I've done the last 2 years, and I've enjoyed it. As a scientist, you really do what you do because you're driven by curiosity. I mean, I remember once my father telling me, you're very fortunate. You go to work every day because you're fascinated by it and because you have a passion for it and you enjoy it. And he said you should always appreciate that because that's not true for most people.
The Institute for Advanced Study in Princeton, New Jersey. Professor Jean Bouguin works here, analyzing and developing mathematical principles.
I'm not an applied mathematician. I am a pure mathematician, so these papers are pure mathematics.
Over the years, he has published papers on a wide range of mathematical fields, from harmonic analysis, nonlinear partial differential equation, combinatorics, the geometry of Banach spaces, to ergodic theory.
There are several things that I liked in math. You can deduce a lot of things from first principles. Just remembering a few things allows you to rebuild a lot of the stuff without having to memorize it. Like formulas, you don't rely much on other people. And you don't rely too much on equipment. I only relied on myself. The field where I have contributed primarily is the area of pseudo-randomness.
Pseudo-randomness is the process of generating random numbers, zeros and ones, the binary bits that make up the language of computers. It has many uses, such as selecting jurors from a given population, compiling statistics, or generating the quote of the day on websites, as well as complex functions such as encrypting secrets to simulating weather patterns. The numbers are pseudo-random because there's a pattern to them, not quite as random as numbers generated from, say, coin flipping.
When people think of random event, they will see someone tossing a coin, and then that, in a way, would produce events that are statistically uncorrelated and are unpredictable. That's another tale. The question is how to produce something that has many features of a truly random coin flipping. And this is where the mathematics comes in and the so-called pseudo-random number generators.
Slot machines spin an endless combination of symbols. They are programmed by a pseudo-random number generator. The software generates billions of zeros and ones per second that decide who wins or loses. The sequence of numbers repeats itself within a certain period. Conventional mathematical theory states the longer the period before a sequence of numbers repeats itself, the more it seems pseudo-random and less predictable.
Long periods are better. Obviously, if you have short periods, you are in bad shape. Of 0 ones.
What Bourgain has done is to show, in theory, shorter periods can yield a sequence that seems random as well.
So my contribution was to show, mathematically, that you still have a lot of randomness when this period becomes much smaller.
The linear congruential generator, invented in 1951, is one of the simplest and oldest algorithms. Here, Bourgain shows how it's used to generate numbers. He picks 3 as his base.
What I will do is multiply this number with itself. So you would have 3, then you would have 3 squared, 3 to the third, and so on. How much is 3 to the power 3? This thing is 27.
To generate a pseudo-random number, 27 is divided by a prime number, say 7. The rounded-off result, 3, is then multiplied again by the prime to get 21. Add 6 to 21 gives 27. 6 is even, so it's labeled 0. An odd number is designated as 1.
So 3 is 1, 2 is 0, 6 is 0, 4 is 0, 5 is 1, because 5 is odd, 1 is again odd.
If 7 is the prime and 3 the base, 6 is the period. That means after every 6th pseudo-random number is generated, the sequence repeats itself. The period 6 is larger than the square root of the prime number 7. Bourgain's contribution is to justify through this equation the period doesn't have to be large to make numbers more pseudo-random.
The problem that I was able to solve is justify good statistical properties when the periods are relatively short.
Pseudo-randomness is one of many aspects of Bourgain's work that earned him recognition, including the prestigious Fields Medal in 1994, the Nobel Prize of Mathematics.
I got a Fields Medal at the age of 40 for a collection of works in ergodic theory, differential equations, and also in harmonic analysis. It took me a while just to analyze how I really compare with other possible candidates at that time. I was in fact not really convinced I deserved the prize. It made me work harder and prove myself. We are at the Institute's lake. After work, we like to change the scenery. One of the keys to remain creative. And at some point you are not productive anymore. You realize your mind is not very sharp, and then you know that you should stop, to try to move to different places. Maybe in town, outside, in a mall, whatever. So see some different faces, different things, and sometimes this is magic.
Jean, aged 56, grew up in a small town in Belgium. He liked maths from an early age.
I would say beginning high school, so age 14, 15. I was a happy child with a normal childhood, nothing like a wonderkind of a precocious child.
He got his PhD from the Free University of Brussels in 1997 and subsequently researched maths in various places before joining the Institute for Advanced Study in 1994. Jean rents this house from the Institute.
Do you often work at home?
In this place, not that much. I may be watching TV and thinking about a math problem. Sometimes I have a little thing to eat.
He lives here for 6 months, and during the summer, he moves back to California to be with his wife and 19-year-old son. Mei-Chu Chang from Taiwan is also a mathematician from the University of California, Riverside.
I'm in California. I have a nice office there at home, and I often take the work with me. Of course, there are times they get irritated. For instance, your wife will ask to go shopping. You say, yes, no problem, but just give me 10 minutes, and you continue to work. Then you go out to do the shopping, and you realize that you more or less forgot what they asked you to buy. You buy something else. They are not always that happy. Altogether, I would say that they are giving me an easy time, and they just let me go when they see that I want to have my head somewhere else. IS is a very unusual place, exactly because we have essentially all the freedom to do what we want when we want. It's very stimulating. Also, when you want to discuss a problem, that there are always people around, not too far away, that you can have a conversation with.
Zeev Rudnik is a mathematician who has collaborated with Bourgain on several research projects.
I've started to work intensively with him about 2 years ago when I first came to the Institute for Advanced Studies. He's an outstanding mathematician. He's done a lot of very different things in many subjects, and they are all absolutely cutting-edge research, and he's someone that people really look up to in many subjects in mathematics. Certainly, his work on pseudo-randomness has been very influential.
Part of Jean Bourgain's job is to mentor postdoctorate research fellows.
I got in the mail Gans collected works. We need to interact with these postdocs, try to help them when they are stuck.
He's fantastic. You know, he's just very nice and very easy to talk to. And maybe there are people who have never approached him before, and so just by reputation alone, they sort of are afraid of him. I could see that happening. He's one of the 21st century absolute giants in mathematics.
Bourgain owes his success to what mathematics has taught him from a young age.
First, I learned hard work, because this is unavoidable. No matter whether you are smart or not smart, in mathematics, you are not going to leave a mark without a lot of hard work.